I'd like to introduce one more conserved quantity. So we've looked at energy, momentum, and now we're looking at angular momentum. And L is the symbol for angular momentum, as I've written here on the top right on the whiteboard section. There are two principal formulas you can use for angular momentum. One of them is L is equal to I omega, so that's moment of inertia times angular velocity. And this is very analogous to how ordinary momentum, P, or you could say linear momentum, is equal to mv, which is mass times velocity. Well, I is kind of the rotational analog to mass, and omega, the angular velocity, is the rotational analog to v, the linear velocity. So in that sense, as we've looked at with other formulas, if you just kind of switch to rotational quantities, they look the same. There is another formula here that applies specifically to a point particle and can apply in some different ways. On the key concepts slide, I have a similar looking formula here, mRV, and there's this perpendicular in both of them, so I should maybe say some words about that. And it says here for linear motion, and the idea is as well, L is equal to I omega. We're going to be talking about an object that has some well-defined rotation axis and is rotating around that axis. But the question is, that I could raise at least, is if an object is not rotating, but maybe simply moving, could it have angular momentum? And the answer is yes, it can. And this formula turns out to work for that. And so that's why I labeled it with linear motion over here. But it turns out MRV also works in a situation where the point particle maybe is part of a rotational system. Maybe it's going in a circle in that sense. And I've kind of shown some of the steps down here where the connection between this formula and the I omega formula, in the sense that if I is equal to mr squared, then following the rigid body rotation formula, L would be equal to mr squared omega. But if I kind of borrow one of those r's and combine it with the omega, that would be a v. So it's mrv, which is the same as this one. And in that type of a situation, this little subscript here for perpendicular winds up not really having any meaning, because if a particle is rotating in a rigid kind of way around a rotational axis, then r being by definition the distance between the object and the rotational axis, that's going to be by definition at right angles to the tangential velocity it will have. So in that situation, you wouldn't need that perpendicular. But it turns out for linear motion, this is maybe a special case of this formula here, mRV sine theta. We're going to see an example that will touch on this a little bit, but I don't want to get too deep into the mathematics of this, but we are going to see an example where you have something that's moving linearly in a way that it still has angular momentum. And one way of looking at that is like if you simply take a point and say, okay, this point is like my origin, or maybe it's really a point that defines the point of rotation, or the rotation axis goes through there. But technically you don't even need to have an axis, I think, for that. But then if you ask, like, can I define an angular momentum in relation to that point for some other object that is moving? And the answer is yes, you can. And does that object need to move in a circle around that point in order to do that? The answer is no, you don't. And in that sense, this formula can be used to describe angular momentum associated with linear motion. So the other big concept, and the reason why we're kind of introducing angular momentum, the reason why it's really special, is it is a conserved quantity, like energy and momentum before it are conserved quantities. And we've seen that not every single system we can imagine would have those quantities conserved. However, if you say that a system is completely isolated, so a completely closed system, a system like that will exhibit energy conservation, momentum conservation, and angular momentum conservation. However, as we saw, let's take, for example, linear momentum. If you have a system that is maybe not like completely isolated from everything else, it has forces acting on it, but the system is defined in such a way that the net force on it is equal to zero. So an example of that is like two cars crashing into each other, right? Where there's obviously gravitational force and normal force that cancel each other out because it's here on Earth. But if we define the system to be the two objects in the collision and there's no other external forces affecting those that don't cancel out, that is, then we could say that for a collision, momentum was conserved. Well, angular momentum has kind of a similar statement. Angular momentum is conserved when the torque on a system is equal to 0. And that's kind of what this summarizing statement down here says. And what that's based upon is what is stated here on the key concepts page. When I wrote the key concepts page, I kind of started with the definitions, but they're a little bit abstract, so that's why I didn't want to quite start with those for the discussion here. But one way of saying like what is really the deep down definition of angular momentum is it's the thing that torque changes. When you apply a torque to a system that tries to make a system rotate, one way of thinking about that is that it is changing the angular momentum of that system. Of course, we've already seen that Newton's second law for rotation says, well, applying a torque to a system winds up causing it to have angular acceleration. But when you have angular acceleration, that is related to the fact that the angular momentum of that system is, in fact, changing. But anyways, that's getting a little bit deep. But it does kind of give the tie-in for why angular momentum might be conserved for certain systems. If torque is equal to 0, and torque is equal to the change in angular momentum over a change in time, when torque is equal to 0, that change in angular momentum would have to be 0, which would tell you it has to be conserved, which can be expressed by saying that whatever initial amount of angular momentum a system has will be equal to the final amount of angular momentum that a system would have.